Hi y'all, this is your second video lecture for section 2.4, so section 2.4b. Reminder of definition of continuity: as long as the limit of f of x as we approach c from the left equals the limit of f of x as we approach c from the right equals the value sitting there, f of c. That would mean that the function is continuous at x equals c. Remember, we can condense these two statements into the single statement. As long as the limit from the left equals the limit from the right, we know that there will be a limit as we approach that c value. So as long as the limit equals the output, we know we have a nice continuous function. For every example today, we're going to be answering all of these questions. The limit from the left, limit from the right. Realize if those two are the same, we will have a limit. The limit will exist and we can state that value. Then we're going to state what f of c actually equals, and then if the function is continuous or not. So for this first example, we have a piecewise function. We have 2 to the negative x and x plus 3, and we have this rule change here. So for every value today, this is your c value, is wherever the rule changes. Okay, what I like to do for all these problems, and I have picked problems where you should be able to graph the functions without a calculator. So I do have that expectation that you know what 2 to the negative x looks like. If you don't, please make yourself a table so you can plug in some points, you can see what the graph would look like. Okay, I know this is an exponential function, but with a negative exponent will give us this kind of guy, going through at 0, 1. And I know I'm only following that rule, though, if x is less than or equal to negative 1. Okay, so I know at negative 1, because I'm including, I know I'm going to have a dot, and I'm just going to be looking at the stuff to the left of that dot. So, oops, my dot disappeared. Let's try that one more time. So here we are, something along those lines. And then my bottom branch, x plus 3, okay, I know I'm going through at 3, so 1, 2, 3. And I'm going to be going up 1 to the right one, up 1 to the right one, or down 1 to the left one. And this will be good as long as x is greater than negative 1. So I know I'm going like this, and I don't know where that dot occurs, but I know for sure that I'm not including negative 1 along that linear equation. Okay, so I tried to draw this graph kind of poorly on purpose, and hopefully I can move it around. So basically I'm trying to see is, where is that dot? Is it going to be above? Sorry, where is that hole? Is it going to be above the dot, or is it going to line up perfectly, and actually that dot is going to end up filling that hole so that we do have a nice continuous function? So we're going to see what happens. So, first question was, what is the limit from the left? So the limit of f of x as we approach, and our c value for this particular problem will be negative 1. So as we approach negative 1 from the left. So as we approach negative 1 from the left, we're getting closer and closer to the value of that actual dot. And that would mean plugging in negative 1 into this equation. So 2 to the negative 1 would be 2 to the positive 1, or 2. So I know the limit as we approach negative 1 from the left would be 2. I want to see if that equals the limit as we approach negative 1 from the right. So as I approach negative 1 from the right, I'd be following along this linear equation, and I'd be plugging negative 1 into this formula. So negative 1 plus 3, that is also 2. Okay. So because the limit from the left equals the limit from the right, they both equal 2. I know that for our second question, the limit does exist. So for part B, the limit of f of x as x approaches negative 1 actually equals 2. Because the limit from the left equals the limit from the right. And this would be how I'd want you to show your work. You're kind of making this statement about continuity, seeing if the left equals the right. And then the last piece of continuity is what I asked for part C, was seeing what f of c equaled. If all three of these pieces are equal, you know you have a continuous function. Now in this particular case, f of c is that dot, which we already knew. So f of c was plugging in negative 1 into this guy, which was also positive 2. So if the limit from the left equals the limit from the right, which equals the value sitting there, for part D I could say therefore this function is continuous. So therefore f, did I call it f? Good. F of x is continuous at x equals negative 1. The because is right here, and this will be your definition. Limit from the left equals limit from the right, which equals the value sitting there. And our sketch, if we had done that accurately, here at -1, that hole and that dot should have been occurring at -1, 2. So if that was completely accurate, both of those, and so my sketch would look something along those lines, if I had drawn it perfectly. Hope that's making sense. Let's try example number 2. So 4 minus x squared if x is less than 1, and x plus 1 if x is greater than or equal to 1. So again, rough sketch here. 4 minus x squared, I think of that as -x squared plus 4. So now I'm going to go up 4, and then I have a nice basic down parabola. And I'm only drawing that when x is less than 1. So when x is less than 1, and because it's less than 1, I know I would have a hole there. So I'm only going to draw this to the left of 1. Something along those lines. And then this guy is x plus 1 if x is greater than 1. So if I was drawing this whole thing out, I'd start at 1, go up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. But I'm only picking it up 1 and after. So I'd have the dot there at 1, and then everything to the left should not be there. So final sketch here, we have this parabola and this line. So this is the question, do these meet up? If they do meet up and it fills the hole, it'll be continuous. If they don't meet up, it will be a discontinuous function. So we want to check, does the limit from the left, so in this case it'll be as x approaches 1 from the left along f of x, does that equal the limit as we approach 1 from the right along f of x? In this case, you can literally just plug in the values into, this is the left branch and this is the right branch. So 4 minus x squared, plugging in 1 from the left, we want to see where that hole would have occurred. So 4 minus 1 will give us 3. So I know that hole is sitting there at 1, 3. And let's check the limit from the right. As we get closer and closer to the right, we want to see where we're getting closer and closer to, so we can plug that into the bottom branch. So x plus 1, where x was 1. So from the right, we're getting closer and closer to 2. Okay? So the limit from the left equals 3, whereas the limit from the right equals 2. So does 3 equal 2? No. They do not equal each other. Therefore, for part B, if I asked you, what is the limit of f of x as x approaches 1, we could say the limit does not exist. So either DNE or no limit. Okay. So for part C, we can clear this up. This would also be part of the continuity discussion, is what actually is f of c? And in this case, we're looking for what is f of 1. So if I plug in 1, where am I? Am I at 2 or am I at 3? I am at 2, wherever the actual dot is. Okay. And then part D, is this function continuous at x equals 1? We would say no, and your reason is this stuff here. The limit from the left did not equal the limit from the right. Okay. And therefore, there's no way you can have a continuous function if you don't have a limit. Remember, the limit would have to have equaled the output there. Okay. All right, so example number 3 and 4, we get a little bit more complicated. We are going to find the k value that actually makes the function continuous. Okay. So again, a nice piecewise linear equation and a linear here. We see this k is standing for some constant. Okay. So here, we wouldn't be able to actually sketch the bottom branch because I don't know how steep it's going to be. That k is essentially our slope. So we need to figure out how steep this line should be in order to make sure that it matches up with this linear equation. Okay. So in this case, we can go ahead and just start with limit from the left as x approaches 1. We want that to equal the limit as we approach 1 from the right. And we also want that to equal the value sitting there. Okay. So if you have to come up with the k value, jump right into your definition of continuity and start plugging in the values, and you're going to end up with some form of an equation. So the limit as we approach 1 from the left, well, to the left of 1 we're using this rule. So I'm going to plug 1 in here. So 0.4 times 1 plus 1. So 0.4 times 1, we're at 0.4 plus 1, we have 1.4. From the right, we're going to plug in 1 into this equation. So k times 1 plus 2, k times 1, k plus 2, k plus 2. So that's all we know right now, is the limit from the left is 1.4. The limit from the right will always be getting closer and closer to k plus 2, obviously depending on what k is. Right? So in order for this function to be continuous, we know that the left-hand limit needs to equal the right-hand limit. So essentially, there is our equation, not on a very straight line there. But if 1.4 equals k plus 2, then we can solve for k. And so I would subtract 2 from both sides. And 1.4 minus 2 would give us a negative 0.6. Okay, so if k is a negative 0.6, we've just found algebraically that that should make the function continuous. Okay. By the way, f of 1, if I plug in 1, realize I would be on this bottom branch here. Okay, so if I plugged in 1 with this k value of negative 0.6, so if that bottom branch truly is negative 0.6x plus 2, if I plug in 1, that would be negative 0.6 times 1 plus 2, negative 0.6 plus 2, that would get me to 1.4, which hopefully you can see would equal that top limit. Okay. So from here, I just want you to sketch to make sure that your answer was actually reasonable. So, it just has to be a rough sketch, doesn't have to be perfect. So this guy here, we were starting up here at 1, and then we had a slope of 0.4, so just a little under 1/2. So we were going up 1 to the right 2, loosely. So up 1 to the right 2-ish, up 1 to the right 2. That would be 1/2. We're slightly lower than that at 0.4. But just as a rough sketch, and then the bottom guy, this k value we figured out to be negative 0.6. So we know that would be a decreasing line. And that would be starting at 1, starting at 2. And this guy we were only picking up to the left of 1. So this was an open circle here and to the left, boom. And then this, we had a decreasing line. We would have started up here at 2. And we would have had a decreasing line of negative 0.6, so going a little bit more than down 1 to the right 2. Boom. Down 1 to the right 2. Boom. And we're going to pick it up only at 1 and after. So I know this one gets a little messy with those decimals, but you do have to be comfortable with using decimals or fractions within your linear equations. And hopefully you can see that these two lines would meet up as long as that k value was negative 0.6. You can imagine if it was too steep or not steep enough, then it would have missed that point. So we had to make it exactly that steep to make sure that it met up. Sorry I'm going so long, y'all. Last example, we want to do the exact same thing. So basically we want to say the limit of f of x as we approach 2 from the left. We want that to equal the limit of f of x as we approach 2 from the right. We also want that to equal the value sitting there at 2. Okay. So essentially what we're doing is plugging in 2 into this equation from the left. So 2 plus 1. We want that to equal plugging in 2 into this equation. So k times 2 minus 5 quantity squared. So negative 3 squared would be 9k. So if the limit from the left has to equal the limit from the right, then 3 must equal 9k. So divide both sides by 9, and we're left with k equals 3/9, which you could totally leave, but let's go ahead and reduce that, and we get a k value of 1/3. Okay. So if k is 1/3, realize that coefficient of 1/3 in front of a quantity squared, like this case, is just telling you how steep or wide your parabola is. And with a coefficient of 1/3, we know that'll be 1/3 as high as it normally was, so it'll actually turn into a wider parabola. So rough sketch here, anything to the left of 2, we were using this rule that we were starting at 1 with a slope of 1, so going up 1 to the right 1, up 1 to the right 1, somewhere along these lines. But here at 2, we were not including 2, so we had a hole at 2, that. And then to the right of 2, if we plug in the 1/3, we're looking at 1/3 times x minus 5 quantity squared. So this is a good discussion. X minus 5, on the inside of the shift, you're going to move to the right 5. So minus 5 looks like it might be to the left, but you do the opposite of what it looks like because it's on the inside. So this will be shifting to the right 5. So I know that my vertex will be at 5, 0. And then a normal parabola would look like that. It's just going to be slightly wider because of the 1/3. So over here at 3, 4, 5, there's my vertex. And because I just said that k equals 1/3 would make this function continuous, I know that it must meet up right there. And because we were including 2 for the parabola, that must have had the filled hole. And then zoom on its way over there. Okay. So part of what I want you to discuss for your whisk discussion tomorrow is to talk about what does f of x appear to have at x equals 2. It's a vocabulary word from yesterday's lecture. Okay. So I hope this made sense and it wasn't too long. Look forward to discussing this with you tomorrow in class.